Hey everyone, welcome to the third video lecture for Module 1. And this will be Module Lecture 1.31. And basically we're going to start with some of the basics of the chemical level of the organization here. So we're just going to cover very briefly some basic chemical properties and those sorts of things. And then we're going to get into pH, which is a little bit more pertinent to what we're going over here. A lot of this stuff I'm going to let your chemistry professor teach to you. Hopefully you've had some sort of background in chemistry, so none of this stuff will be new to you. If I'm not mistaken, either having chemistry or biology is a prerequisite for this course, so this shouldn't be any sort of new information and should just be a rehash. We should be able to just roll through this stuff because a lot of it isn't too necessarily important for what we're going to specifically cover, but as you move into further levels of physiology, further levels of medicine, if you don't have this basic understanding of how molecules and atoms and elements interact with one another, it starts to make things get a little bit more complicated later on. So we're just going to touch on it. If you need more help with it, let me know. I'd be happy to help you, but a lot of this stuff you should already know, and then you'll learn in Chemistry 101. So chemistry is the study of matter, and matter is anything that takes up space and has mass. Mass is technically the quantity of matter in an object, and on Earth, mass equals weight. And that has a little bit of gravity associated with it. So matter typically exists in 4 states. I know that's pretty shocking. Most of you know the 3 states, which are solid, liquid, and gas, but there's actually a 4th one on there as well, in a special case of a plasma. A plasma is sometimes classified as a subset of gases, but it behaves differently. Essentially, a plasma, or in a plasma, the atoms are ionized, meaning that they're strongly influenced by electromagnetic fields. I won't go over what an ion is later if you don't already know, but you can read the case there as well. Basically what happens is it behaves differently as a gas. While a gas will not inertly react with any sort of electrical field, either positive or negative, a plasma is going to react strongly with it. And you can see some areas where you'd see some plasmas a lot of time, the exteriors of stars, sometimes in lightning strikes and television screens. You've heard of a plasma TV? This is where it came from. However, if you're thinking about it, blood plasma is very different. Blood plasma is the liquid portion of blood, and we're talking about an electrically charged gas when we talk about plasma in this sense. Water is the only substance that exists in all 3 states of matter at temperatures that are compatible with life. If I ask you a question, the importance of water, this would be your definition of that. Matter is composed of elements, and elements are substances whose molecules contain only one type of atom. 98% of all living matter is composed of 6 elements. You can see them listed here. We used to use the phrase schnapps. I don't want to speculate as to who came up with that, but schnapps to cover the 6 major elements in physiology, or at least in chemistry. But it's a little bit different for A and P. Instead of the S portion here, we're going to include a calcium portion. And there are 11 principal elements that are add the most substance to body weight. There's also several trace elements that we'll get to as well. Here's the periodic table of elements. I'm sure that you've seen this before at some point in your career. Here you can see the most abundant elements in the human body. I would strongly encourage you to know the top 6 of these. So I would know the element and the symbol. They're not going to make you necessarily recall the percentage of that element in the body, but you should know the relative percentages as far as how the top 6 relate to the rest of the trace elements in the body. So atoms and molecules are the basic principles of matter. Chemicals are composed of atoms. Atoms are the smallest stable subunit of matter. There are several smaller subparticles of matter and of atoms, but none that you really need to know to until you get the advanced level of physics. And atoms are composed of subatommic particles, the largest of which are the protons, neutrons, and electrons, and hopefully you've all heard of those before at some point in time. Going back real quickly, protons are going to have a positive electrical charge, neutrons are electrically neutral, and electrons are going to have a negative charge. You're going to find protons and neutrons in the nucleus of the atom, and electrons are typically in a cloud around those, occupying some level of electron ring or electron subset. So atoms can divide it into regions. The nucleus of an atom lies at its center, and like I said, the nucleus contains one or more protons as neutrons as well, and the mass of the atom is primarily determined by the number of protons and neutrons that exist in that nucleus. The mass of that atom helped to classify it on the periodic table as well. And again, electrons are orbiting typically in a cloud. So with that said, we can discuss two models of the atomic structure. And the planetary model, which is shown at the top here, the electrons of helium, which is in the middle, are depicted as a ring. A lot of times this is what you're going to see in the typical planetary model or the Bohr model. But in the electron cloud model, they're depicted more accurately as just in a cloud around the nucleus. And the reason for that is electrons are moving very, very quickly in orbit around these nuclei, and we have no idea at what particular point in time or where an electron is at that particular time. So the more accurate depiction is just a cloud around that. Here you can read about electrons and valence shells. Again, they orbit in a cloud, and it depends on the number of electrons as well as the energy of that electron as to determine what valence shell it's in. You should have studied this in Chem 101, but a brief overview of it is atoms can have several valence shells as the energy level increases. The first valence shell can hold about 2 electrons. As you move up in size and quantity of electrons, you increase to 8, and then you'll start to get to the rule of octets, where an electron will try to fill its octet valence shell before electrons start to move to the next level. So a full valence shell will represent an electrically stable atom. So when atoms interact, they form larger, more complex structures called molecules. All matter is composed of varying arrangements of atom, and those variations in matter and characteristics result from types of atoms and the ways that they interact. Atoms can normally contain equal numbers of protons and electrons so that they can remain electrically neutral, because one way or the other will influence it electrically. The atomic number is equal to the total of protons in an atom. The mass number is equal to the total of protons and neutrons in an atom. And the element is a substance composed of only atoms with the same atomic number, as we discussed in slide 1. Isotopes are atoms with the same number of protons but different number of neutrons. They have identical chemical properties but vary in the mass number themselves. Some of them will typically have different names, but the major difference in them is how much they weigh. This slide just covers the atomic weight of the atom and how it's measured in Daltons. I'm not going to quiz you on this type of stuff, but I just wanted you to know that it was there. So most atoms that occur in nature are electrically neutral, meaning that every positive proton is balanced by a negative electron, and when electrons occupy an orderly series of energy levels within the electron cloud. This goes back to the energy levels that I spoke of earlier, that the outermost energy shell, or its valence shell, is the surface, and that's how it determines how it interacts with other atoms. Again, brief overview of the electron shells. Getting into ions here. So atoms that have gained or lost electrons are no longer electrically neutral. Ions are very important when we get to physiology. Losing an electron means that fewer electrons, i.e. negative, than protons, positive, means a net positive charge. It's called a positive charge, or a cation. So a missing electron equals a charge of +1. This is kind of a difficult concept for a lot of first-year chemistry students to understand. The loss of an electron means that you are positive. So because an electron is a unit that has a negative charge, if you lose a negative charge, you become more positive. And when we talk about this stuff and becoming an ion and that sort of thing, we can only lose electrons, because if we were to lose a proton, we would change the element. So if I ask you a question about what would happen if you changed a proton, you would tell me that that couldn't happen because you would change what the element actually is. anions are the opposite of cations, meaning that you're gaining an electron. So you have more electrons, i.e. a negative charge, versus protons, which is a positive charge, which is going to give you a net negative charge. This is called an anion, or give you a charge of -1. And you can continue to have that as you go forth by adding electrons, i.e. -2, -3, and -4. So a molecule versus a compound. A molecule is a chemical substance consisting of two or more atoms that are held together by covalent bonds, and a compound is the same thing that's made up of two or more atoms with different elements. Mixtures are substances composed of combinations of elements and or compounds. In a mixture, there is no property change. Okay, they are mixed together, but they are not chemically bonded. For example, air, soil, salt. One of the big examples that I used to give here in some of my other classes is Kool-Aid. Kool-Aid is a mixture. I'll put sugar, water, and a Kool-Aid mix in the jar, stir it up, and it's still those separate things, but they're all mixed together. If we were to give it enough time, those things would filter out and become separate again. We'll discuss a couple of types of chemical bonding here. Ionic bond is one of the most common types of bonds. It's created by electrical attraction between cations and anions, and involves the transfer of one or more electrons from atoms to achieve some sort of stability. Think here sodium chloride or salt formation, where a negative chlorine atom will accept a electron from a positive sodium atom. The covalent bond involves sharing of electrons, so there's no donation or loss or gain of electrons, but the atoms share the electron between the electrical clouds. And these are very, very strong bonds. You can have single covalent bonds, double covalent bonds, you can have triple covalent bonds, and these are things that you'll start to see more as you get into higher levels of chemistry, biochemistry, and things like that. You can have what's called a polar covalent bond, where there's unequal sharing of electrons between atoms. An example here is water, is one of the most common types of examples, where you'll have electronegativities that determine your polar covalent bonds in this example. So you'll take hydrogen and water, and with water being more electronegative than the hydrogen, the electrons are going to get forced towards the water molecule more, which is going to create a negative or a slightly more negative charge towards the other end of the water molecule, where there's going to be a slightly more positive charge to the hydrogens, which are getting the electrons pulled away from it. A non-polar covalent bond, those electrons are shared equally between two electrically equal elements. And polarity just talks about what we talked about there, where you can see the partial positive charge here, partial positive charge here, and the partial negative charge here. It creates what's called a dipole moment, but that's something you don't really need to know until you get into organic chemistry. Hydrogen bonds are something that are very important when you talk about how water interacts with one another. And basically what happens is, because of those partial charges, you start to get that partial negative charge on one oxygen, with that partial positive charge on one hydrogen, and that partial positive and negative, we know those two attract to each other, so it's going to form a small semi-weak bond between those two molecules as they start to get pulled together, and it's one of the things that gives water some of its unique properties, such as surface tension. So as I said, it's the attraction of small positive charges on hydrogen atoms of a polar molecule to a negative charge on an atoms on a polar molecule. It can change the shape of molecules or pull molecules together. We see this most consistently when you see phase changes in water. For example, when you get ice, ice will freeze those hydrogen bonds in place, which allows water to solidify. In liquid, what gives it that kind of liquid property that we're all used to is the constant formation and breaking of those hydrogen bonding. That just highlights what we just talked about. In a chemical reaction, new chemical bonds form between atoms, or existing bonds between atoms are broken. So when those chemical bonds break, it's called a chemical reaction. This changes occurs as atom and the reacting substances called reactants are rearranged to form different substances called products, and all of the reactions underway in a cell and tissues of the body at any given moment constitutes its metabolism. So if I ask you the definition of metabolism, it's the sum of all chemical reactions that occur in the body. Those chemical reactions allow the body to produce energy, and that allows our cell to do work. And work is the movement of an object or change in the physical structure of matter. There are several different forms of energy. You guys, I'm sure, learned this when you were in high school or in some sort of physics class or something like that. But you have kinetic energy, which is the energy in motion. Potential energy is energy that's stored. And the conversion of kinetic energy to potential energy and from potential energy to kinetic energy, it's never 100% efficient, but it is what helps to release some of that chemical property. There are a few different types of chemical reactions. We're not going to cover this stuff in this course, but just so you know, you have a synthesis reaction, which is taking two substances and putting them together. You have a decomposition reaction, which is taking one substance and forming it into two. And then you have a displacement reaction or exchange reaction, where you'll take one substance, take a part of that one substance, and formulate it to another one. A lot of times you'll see single displacement and double displacement, and that's shown with letters instead of the way it's written here. You'll have AB plus CD, and then that will turn into, if you all remember FOIL from algebra and geometry in high school, you'll have AB plus CD equaling AD plus BC. Most chemical reactions do not occur spontaneously. They require something that serves as a catalyst to help move that energy along. In a lot of physiological processes, we talk about an enzyme that helps to lower the activation energy in order for it to be able to do that. Just a brief overview of that activation energy. A lot of time it requires a lot of energy to get something to actually happen. So what an enzyme does is it'll come in and it'll take this amount of energy that's required and push it on down to about this right here, to where it's easier to get over that hump and to create a stable product. So a series of complex reactions that occur in the body we'll call eventually a metabolic pathway. This is a very complicated overview of a metabolic pathway. If you take a real good look at it, I'm sure you'll understand what it is coming to the TCA cycle. If any of you take organic chemistry later on, you will grow to hate this. Each reaction will interlock with the next step, and it just turns into a sort of what the name implies is a pathway of those chemical reactions to get to the final product. Oftentimes, especially when we talk about physiology, enzymatic reactions are essential to the process of making metabolites or things that our body needs to function. Water is considered the universal solvent because of those polar properties that water has. It's able to pull apart both positive and negative ions from other items. Polar substances are usually hydrophilic. There are a couple weird cases, but we won't talk about that here. And the roles of hydration spheres in the ionization or dissociation of an ion compound in a solutions of an organic molecule contain polar covalent bonds. So you'll see this partial positive charge of the hydrogen here starting to attack the negative chlorine atom here. You'll see the partial negative charge starting to react with the positive sodium charge here, and eventually it's going to cause that to dissociate or separate from each other to equal out some of the energies. Non-polar molecules are hydrophilic, or my apologies, hydrophobic, meaning that they're afraid of water. They're going to move away from water. And these are going to be things like your fats and oils, your lipids when we get into the next section. Body fluids contain electrolytes, and the movement of sodium and chlorine ions dissociate from the electrolyte sodium chloron when subject to an electrical field. So you'll start to see positive ions move towards a negative charge. You'll start to see negative ions move towards a positive charge. In this table down here to the right, you can see some examples of some electrolytes and the ions that are released when these dissociate. Water is also important for pH regulation. The dissociation of water molecule into hydrogen and hydroxide helps contribute to the pH levels. I'm sure that you're very aware of pH. However, what we'll talk about here is as you As you decrease pH towards 0, you'll start to become increasingly acidic. As you start to increase pH towards 14, you'll start to become increasingly basic. We consider normal physiological pH to be 7.4, and the pH of your blood ranges anywhere from 7.35 to 7.45. Now, when those change, a very small change can cause very, very big problems when we're speaking in physiological sense. Acidosis is an abnormal product that happens when your blood dips below that 7.4 range, and alkalosis happens when you move above that 7.4 range. Acids are electrolytes that release hydrogen ions and are considered to be proton donors, so they'll readily give up that hydrogen. They, like I said before, they have a pH of less than 7 and have varying degrees of strength. Bases are electrolytes that release OH negative ions or hydroxide ions and are considered to be proton acceptors, so they will take that proton from an acid and use it to form something else. A lot of times you'll start to see acids and bases mix when they get into solution, typically because if acids are willing to donate a proton and bases are willing to accept a proton, you're going to have an interaction between those. A lot of times we call that a neutralization reaction if the relative strength of the acid and the base are similar. You'll get, as I said, what's called a neutralization reaction, where you'll have the formation of some sort of property. Sometimes it's a salt, and then water is a byproduct. Salts are electrolytes that dissociate to form two of the most notable ions in current conduction. So there are more than one type of salt. Sodium chloride, is noted here, is not just a salt. A salt can be a combination of anything from the first column on the periodic table and the seventh column on the periodic table. So any combination of those elements can form a salt. Buffers are compounds or solutions or something else in the body that help to resist abrupt and large swings of changes in pH. So essentially, when pH begins to rise and fall, they'll either bind hydrogen ions or bind hydroxide ions or release hydroxide ions to regulate that pH to help reduce drastic changes, because drastic changes in pH, as we talked about earlier in the example that we gave in class, can cause major physiologic problems.